This lesson is going to be on finding the absolute and relative extrema on a graph. Before we get to that, before I start talking about that, I'm actually going to turn my iPad so we can only just see this part. I just want you to take a moment to review the important parts of the first and second derivative test. So this first thing I want you to do is just pause this video for a moment, and I want you to fill in the blanks here. So in the first derivative test, a function has a relative minimum if, and then there are two things that must be true. Similarly for a relative maximum, and then do the same thing for the second derivative test. Using the second derivative, what two things must be true for there to be a relative minimum, what two things must be true for a relative maximum. So pause the video, see if you can fill those in, and come back. Okay, I hope you took the time to actually do that, to pause and determine these criteria. So let's look at the first derivative test. What must be true for the first derivative test is that the first derivative must equal 0 or must be undefined. So in other words, what are the critical numbers? And the same is true if we're looking for a relative maximum. F prime of x must be 0 or undefined. So those are the criteria. We're looking for those critical numbers, the places where the function could have a relative minimum or a relative maximum. Well, once you find those critical numbers, then to determine if there is a relative minimum, f prime of x must change from negative to positive. If the first derivative changes from negative to positive, that means the original function changes from decreasing and then to increasing. And that would make a relative minimum on the function. And then similarly, f prime of x must change from positive to negative for a relative maximum. That way, the original function would be increasing and then changing to decreasing, making the function have a relative maximum. Okay, now the second derivative test, a function has a relative minimum if, same criteria as above, and I'm going to stop writing all of this out. Same criteria above. We're going to find those critical numbers where the first derivative is either equal to 0 or the first derivative is undefined. And I'll paste it here as well. The difference here with the second derivative test is that at the point of where the derivative is undefined or equal to 0, to find a relative minimum, we know that the function must be concave up. So we know that the second derivative then must be greater than 0. That makes the function concave up, and at that critical number there will be a relative minimum. And then other way around, the second derivative would be negative, meaning the original function would be concave down, making that critical number a relative maximum. Okay, that's a good review. Now let's talk about absolute versus relative. So I'm going to put this function in here too. Some textbooks, some notation use the word global and local versus absolute and relative. But an absolute or a global extrema is the highest or lowest point on a function over a closed interval. And then relative extrema is what we've been looking at so far. It's a turning point on a function. So that's where the derivative changes from positive to negative or negative to positive. So if I look at this function here, I want you to think for a moment, does this function have an absolute maximum or an absolute minimum? And does this function have a relative maximum, a relative minimum? Take a moment to think about it based on the definitions I gave you above. Okay, looking at the relative extrema, the turning point, that's where the slope changes from positive to negative, negative to positive. So there are two relative extrema here. We have a relative maximum here. That's where the function turns around, slope changes from positive to negative. And here's a relative minimum. We have a turning point, that's where the slope is changing from negative to positive. Now, as far as absolute extrema, the highest or lowest point of on a function over a closed interval. Well, we can see that the domain of this function is on the interval, the open interval from negative infinity to positive infinity. This is not a closed interval. There is not an absolute highest point or an absolute lowest point on this function because this function domain is infinite. So what I'm going to do now is restrict the domain and try to determine the absolute extrema for this function on that closed interval. So let's take a look here. On the interval, so on the closed interval, from 0 to 8, I would like you to find the relative minimum and maximum and the absolute min and max. So when I say this is on a closed interval, I'm saying that we are only looking from this part of the graph to, let's see, 1, 2, 3, 4, 5, 6, 7, 8, to this part of the graph. We're not looking at anything beyond those values, where x is 0 or x is 8. So take a moment, see if you can answer these four. Is there a relative min? Is there a relative max? Is there an absolute min? Is there an absolute max? If so, where is it? So pause, go take a look. Okay, welcome back. So let's talk about relative min and max. I can see from the graph the first time I looked at it, the relative minimum, relative maximum has not changed. There's still a turning point in the function at those points. That is where the slope is changing sign from positive to negative or negative to positive. So we still have a relative minimum at the ordered pair, at the ordered pair 5, negative 1. We still have a relative maximum at the ordered pair 1, 4. That part has not changed. Now let's look at the absolute minimum, absolute maximum. So I'm looking at the highest and the lowest point on this closed interval. So what I can see is on this closed interval, the lowest point of this function happens to also be the relative minimum. So the absolute minimum is also the point 5, negative 1. The absolute maximum actually occurs at two different points. This point here and this point here is the absolute highest value for this function on that closed interval. So I have two different points for the absolute maximum. 1, 4 and 8, 4. So the purpose of what I just did was to show you that absolute extrema can show up at two different locations. Absolute extrema can show up at not only the critical numbers, but also at the endpoints. So let's just define this here. Absolute extrema can occur at critical numbers and or at endpoints on a closed interval. Something really important to note. This isn't a really mind-boggling, it's not a really difficult concept, but it's an area of misconception. It's a place where students will make a mistake. They'll forget to also check endpoints for absolute extrema. So just keep that in mind. Visualize this graph, and that'll help you remember. Okay, something that you need to know exists is this extreme value theorem. This is saying that if a function is continuous on a closed interval, then there is both a maximum and a minimum value on that interval. Guaranteed. That is the extreme value theorem. Always a minimum, always a maximum on any closed interval, as long as the function is continuous. Something you need to know, nothing really important, just know that this exists. Okay. I would like you to determine whether each point on this graph is absolute max or min, relative max or min, or neither. I just want you to label each one. Is it an absolute max, absolute min, or neither? Go. All right, welcome back. Point A, I'll start there. Point A, it's not considered a turning point because the slope is not changing before and then after. So this is not a relative min or max. However, this is the absolute lowest point on the function. This is a relative minimum. Sorry, I just said absolute and I wrote relative. This is an absolute minimum. Point B is a turning point. The slope changes from positive to negative. This is a relative maximum. Is it also an absolute maximum? No, because there is actually a point higher than this point on the graph itself. So this is a relative maximum. The point C, that is not a turning point. The slope is not changing from positive to negative or negative to positive, nor is that the highest or lowest point on the function. So this is neither, it's not extrema. Point D is a turning point. The slope changes from negative to positive. However, that is not the lowest point on the function. So this is a relative minimum. Point E is also a turning point. The slope changes from positive to negative, not the highest point. This is a relative max. Point F, the same. We change from negative to positive slope, but not the lowest point, relative minimum. And then point G is a little weird. It's not a turning point because we're not changing slope. Nor is this an absolute max or a minimum because the point G actually does not exist on the graph. So that point G does not exist. This is neither a relative extrema nor an absolute extrema because the point does not exist. All right, finally, let's put this to the test. Let's just do an example. I'm asking you to find the absolute extrema on the closed interval for this function. So remember, we talked about that absolute extrema can occur at critical numbers as well as endpoints. So I'm going to find the critical numbers for this function. To do that, I will find the derivative, setting this to 0, and factoring. If I take out 8x squared, that leaves me with x minus 3. So what I can see here then is for my critical numbers, x will equal 0 or x will equal 3. Keeping in mind the domain from -2 to 2, x equals 3 is outside of the domain. So it is not a potential for an absolute max or min. All right, so what I need to know is which of these points, 0, -2, or 2, is the highest or the lowest. And when we're looking at how high or low it is, we're looking at the y value. So what I'm going to do is plug each of those values into the function, figure out which one has the highest y value, which one has the lowest y value. That's all we need to determine absolute extrema. So if I look at g of -2, g of 0, and g of +2. Okay, so I will plug -2 into the function. -2 to the 4th is 16 times 2 would be 32. 2 to the 3rd is -2 to the 3rd is -8. -8 times -8 makes this positive 64. So this y value is 96. That's a pretty high y value. Right now that seems like a pretty good candidate for the absolute maximum. Let's plug in 0. 0 to the 4th minus 8 times 0 squared. Sorry, 0 cubed. I was looking at the derivative. This is 0 minus 0, so we have a y value of 0. 0 is definitely less than than 96, so potentially right now that 0 is the absolute minimum. But let's try plugging in +2, see what happens. So if I plug in +2, I get 2 times 2 to the 4th minus 8 times 2 to the 3rd. 2 to the 4th is 16 times 2 is 32. 2 cubed is 8. 8 times 8, negative 64. So I get a y value of negative 32. So I have ordered pairs here. The ordered pair for this point is -2, 96. This one is 0, 0. This one is 2, negative 32. From this, I can tell which point is the highest on the function, which point is the lowest on the function. So in this case, this point, this end point, is the absolute maximum. And the other endpoint is the absolute minimum. So in this case, the critical number did not happen to be the highest point on the function, but it could have been, it just wasn't in this case. Okay, that's absolute versus relative extrema. That's an example of how we test. Go give it a shot.